Rodrigo came to us about 5 years ago now, after getting a bachelor's degree from Swarthmore. In those intervening 5 years, he's completed a large amount of research, and we're probably only going to get to hear a small fraction of that today, unfortunately. But it's going to be an exciting tour de force of all these issues to do with exoplanets, small ones especially orbiting the low-mass stars. And for those of you who aren't familiar with the exam format, Rodrigo is going to be speaking to us for about 45 minutes about the various topics that he's worked on. At that point, questions are encouraged from the general audience. At that point, the audience will be dismissed, and a few of us will hang around a little longer and talk to him a little bit longer. But with that said, I think I'll just pass it off to Rodrigo. Please take it away.
Thanks, Rory. Pleasure to be here. So my topic is a bit broad, so it's by no means comprehensive, but I'm going to discuss the evolution, detection, and characterization of planets in the habitable zones of low-mass stars. And to help me, Jake gave me this anti-aircraft laser pointer. It's quite bright, so I apologize. For reasons that will hopefully be obvious soon, this talk is divided into H parts. The first few parts, I'm going to discuss some aspects of the evolution of these planets around low-mass stars. We're going to see how they're quite different from the evolution of planets around the sun or solar-mass stars. I'm going to talk about efforts I've done to detect these planets using current instrumentation, and efforts to characterize these planets using future instrumentation. And again, not comprehensive, but give you a glimpse of stuff in each of these topics. Okay, so in the way of a little bit of introduction, one of the really cool things about the time we live in is the number of exoplanets we discover has been doubling at every 27 months or so. So this is kind of like the Moore's law for exoplanets. We started with the first discovery in the early 90s. Today we know of several thousand, about 5,000 exoplanet candidates. If it continues at this rate, by 2034 we will know of 1 million exoplanets. It does show that we live in a very special time in exoplanet science. And a lot of this is due to the Kepler telescope, which I showed here on the right, which hunts for exoplanets via the transit method. I'll talk a little bit more about this later, but basically we're looking at the dip in the flux received from a star as the planet crosses in front of it over the course of its orbit. And the amazing thing is that only a small fraction of planets will ever be seen to transit their star, just because of the low geometric probability of their orbits being aligned with the line of sight to Earth. But still, we're finding thousands of these, which means exoplanets are extremely common. The other bit of introduction that I need to tell you about is the habitable zone. Most of us are familiar with this. It's that region around a star where liquid water is possible on the surface of a terrestrial exoplanet. And now the habitable zone changes depending on the mass or type of the star. For a G-dwarf like the Sun, we have the habitable zone out here at about 1 astronomical unit where the Earth is. I've purposely not put numbers here. This is mostly a qualitative slide. We can see that there are different definitions of the habitable zone depending on how optimistic or conservative you are. And there's some evidence that Venus and Mars may have been habitable in the past, or could have been. And so the habitable zone can be a little wider than the physics actually tells us currently. But the interesting thing that I want you to notice here is that for lower mass stars, the habitable zone is much closer in. And this is a logarithmic axis. So that around these M dwarfs, which are low mass stars, going down to about 10 the mass of the Sun, the habitable zone can be almost 100 times closer in than the Earth is to the Sun. And I'll come back to this point later, because since this talk focuses on planets around M dwarfs, it's important to understand why M dwarfs are so cool for exoplanets. And so this is just kind of a word cloud of reasons we would care about M dwarfs and their planets. M dwarfs comprise most of the stars in the galaxy, about 70%. The closest stars to Earth are M dwarfs, Proxima Centauri, and a little farther out, Barnard Star, and several others. When you're hunting for exoplanets via the transit method, it's really cool that your star is small, because that means that the signal will be larger. Your planet blocks a larger fraction of the star. And so you see a deeper signal. You will also see deeper secondary eclipses because of the more favorable planet-star contrast. The short periods of planets in the habitable zones of these stars mean that they transit more often. And so if you stare for a given amount of time, you will see a lot more transits, so you have a lot more data. And a ton of other reasons. The other big one is that M dwarfs have tons of planets. We're starting to find that the number of planets in the habitable zone of M dwarfs, the fraction of M dwarfs with planets in the habitable zone is larger than for higher mass stars. And so that's awesome. So we want to look around M dwarfs for planets in the habitable zone. However, we need to keep in mind that M dwarfs are very different stars than the sun. It's not just their masses that are smaller. The actual physics of their high energy emission, their flares, and just the way they evolve is very different. And so we need to keep that in mind when we're searching for these planets and trying to understand whether or not they're habitable. And so with that, we'll get into the first science part of my talk, which is mirage Earths. And so just to begin here, what I've plotted here is the evolution of the inner edge of the habitable zone as a function of time for the sun. Now, when stars form, they form from giant molecular clouds and quickly contract on cosmological timescales, and eventually start fusing hydrogen in their cores. And at that point, they reach a somewhat stable luminosity that continues for billions of years. And so, above this line is where the habitable zone is. Below this line is closer to the star, hotter, planets not habitable. If you imagine where the Earth is today, close to the inner edge of the habitable zone, and then you project this backwards in time to when the Earth formed, we are comfortably reassured that the Earth has always been in the habitable zone, which is great for life, and here we are today. So that's great. But one of the points that I made earlier is that low-mass stars evolve very different. If you look at a similar evolution track for the inner edge of the habitable zone around low-mass stars, you can see that it's markedly different. Low-mass stars take much longer to contract from giant molecular clouds and reach what we call the main sequence, which is when they start fusing hydrogen in the cores. And so if we do the same thought experiment around 1/10 of a solar mass star, and we put an exo-Earth right near the edge of the habitable zone there today, and we project it back in time, we can see that for a large portion of its lifetime, this planet has been interior to the habitable zone. And if you have a keen eye, you'll notice that this planet formed earlier than the Earth did, and that's because that's one of the consequences of a lower mass star. The habitable zone is closer to the star, so you're deeper in the gravitational potential well of the star. Orbits are much faster, and so accretion timescales are much shorter, planets form. And so that's even worse.
It's not a large portion, proportionally it's not a large time, right? I mean, it's a large scale.
It is large.
But is it more that it's a critical time, and that's when there's still a critical?
So for these lowest mass stars, it can be up to 1 billion years. But you're right, I mean, these planets can be many billions.
Yeah, but if it's already lost, if all the water's already boiled off.
Right.
Yeah.
So the first few hundreds of millions of years are critical for that reason. And that's exactly what I studied. So the problem with being interior to the habitable zone is that your surface temperatures are so high that water is not stable. And if your water is all evaporated in your atmosphere, it can slowly or quickly be picked off by stellar high energy radiation, which dissociates water into oxygen and hydrogen. And hydrogen, which is really light, essentially floats up to the top. And all this high energy radiation from the star deposits a lot of energy in the upper layers of the atmosphere, which causes it to adiabatically expand. And that can drive a hydrodynamic wind, which carries most of this hydrogen to space. And so planets can lose large fractions of their water inventory early on if they're interior to the habitable zone and the star is emitting a lot of higher energy radiation, which M dwarfs do. And so if we go through the numbers and the equations, we get something that looks like this. Now what I've plotted is the amount of water that is lost from planets around low mass stars as a function of stellar mass. So the sun would be up here, these are low mass M dwarfs, and fractional position in the habitable zone. And so essentially these dashed lines are the conservative limits of the habitable zone. And so what we can see is that planets that are close to the inner edge of the habitable zone around these low-mass stars are losing something like 10 Earth oceans of water during these first few hundred million years when they're interior to the habitable zone. And as you go to larger distances from the star, it's not as bad, but it's still significant for these low-mass stars. As you go up to higher-mass stars, it's much better. These planets lose much less water because these stars form very quickly. What I've plotted here on the right is oxygen. So remember I said that you're getting the dissociation of water molecules, which causes hydrogen to escape. The oxygen molecules the oxygen atoms can also escape. They can be dragged along hydrodynamically. But even when you account for that, you still have a lot of oxygen remaining in the planet atmosphere. Now, a lot of that oxygen can react away. Oxygen is extremely reactive. It can react at the surface. It can react with other compounds in the atmosphere. And so it's not clear at all that all or even most of this oxygen is going to remain in the atmosphere, but some of it can. And we can see that throughout most of the habitable zone, you're actually building up the equivalent of several hundred bars of oxygen. Now, 1 bar is the atmospheric pressure of the Earth, so this is a lot of oxygen. And again, some of this could stay in the atmosphere, which is problematic because when we think about searches for life around other planets, we would like to believe that if we find oxygen, it means there's photosynthesis and there's life. But there are abiotic mechanisms that produce oxygen, so we need to be careful of those when searching for biosignatures in exoplanets, especially around envelopes, where this process could lead to the production of oxygen. So this brings me to the next part of the talk, which is essentially the flip side of what I just told you. So I just told you M-dwarfs are terrible for habitability because they can desiccate terrestrial planets. But if you consider the scenario on the right, where you start with a planet that's not terrestrial, you start with a planet that has a significant hydrogen envelope, something like a mini Neptune or a hydrogen-rich super. What I wanted to investigate was whether that could actually lose its hydrogen envelope and form something that's more terrestrial. So investigating a pathway to habitability around M-dwarfs that takes advantage of the fact that these stars cause vigorous hydrodynamic escape. Now, a mini Neptune isn't habitable, right? The surface pressure and surface temperature is way too high because of all that hydrogen. But once you lose that, you could potentially form an evaporated core in the habitable zone. Now, we know that planets like Neptune in our solar system and like the moons of Jupiter and Saturn, which form far from the star, far from the sun, have a large fraction of ices, especially water ice. And so we might expect that these exoplanets that are Neptune-like also formed with lots of ice. Once you evaporate all that hydrogen, you have ice, which melts, and suddenly you have a water in the habitable zone, which could be a potentially habitable planet. So I just wanted to investigate whether this formation scenario is at all plausible. And so in work with Rory Barnes and Vicki Meadows and collaborators, we looked at how stellar evolution, atmospheric escape, thermal evolution, and tidal evolution could act together to potentially form these habitable evaporated cores. Now, I talked about stellar evolution and atmospheric escape recently. Thermal evolution is important because gaseous planets, when they form, they're inflated. They still have all that energy from the accretion process that causes the radii to be very large. And slowly they cool with time. They radiate that energy and contract. But early on, low-mass planets that have significant hydrogen have very large radii. And the reason that's important is because suddenly you have a much larger cross-section to the stellar radiation that's driving escape. And so this can actually accelerate the escape process. Tidal evolution is also important because if a planet forms at high eccentricity, what can happen is tidal forces acting to distort the planet away from sphericity that cause the familiar tidal bulge that we see on the Earth through the moon. These tidal forces can actually cause friction inside the rigid body of the planet, which tries to maintain the bulge in a certain direction. Rotation tries to point it towards the star. That generates friction, dissipates energy, which causes the eccentricity to decrease, the semi-major axis to decrease, and essentially affect the orbital evolution of the planet by dissipation of this energy in the planet's core. And so that can cause the distance of the planet to the star to change, which can change the atmospheric escape rate. So these are all important aspects to consider. Here's just a typical, well, I wouldn't say typical, a sample evolutionary pathway from one of these planets. So you can see that what I've plotted up here is in black, the mass in the envelope of the planet. So you start off with something like 1 Earth mass of hydrogen. A lot of it quickly escapes due to Roche-Loeb overflow, which is where you're past the point of gravitational influence of the planet. The star's gravity actually strips off the gas early on, and then you have a hydrodynamic escape phase, which operates on timescales of tens of millions of years. And so that can cause further loss of that hydrogen, and eventually you completely remove it. And you can see that at the same time, the radius of the planet's evolving, the orbit of the planet is evolving. This is the semi-major axis in black and the eccentricity in red. You can see how the star is evolving simultaneously. The luminosity of the star is decreasing as the star contracts. And the high energy, the radius of the star is increasing. So all these things conspire to allow, in principle, these planets to form from the evaporated cores of these hydrogen-rich planets. And so what we can do is we can ask where in the habitable zone can these evaporated cores form? And depending on different assumptions of the regime of the hydrodynamic escape or the initial eccentricity of the planet, you will get these lines to the left of which evaporated cores are possible, to the right of which you're too far from the star for hydrodynamic escape to be efficient enough to completely strip them. Now the details of this aren't terribly important, but you can see that for some of these lines, the region to the left of these lines intersects a large portion of the habitable zone. So in principle, these planets are possible in the habitable zone. Now there's been recent work showing that for these higher mass stars, they're actually not in a hydrodynamic escape regime. And mass loss is actually much slower than what I predicted in my paper. But around these low mass stars, the gist is that if you are about an Earth mass and you have a ton of hydrogen, you can lose all of it in the habitable zone. And so under certain conditions, these evaporated cores are possible. Potential formation scenario for a water-rich planet in the habitable zone. Okay. So with that, hard transition to detection. So I talked a lot about how habitability of these planets is interesting for sure, and we want to find more of them so we can study it and figure out whether in fact they're habitable. And so a lot of the detection of these planets is currently being done with the Kepler telescope, which I alluded to earlier. So this was launched in 2009. It stared at a patch of the sky, about the size of your extended thumb. It stared at that patch of the sky for 4 years, monitoring the brightness of 150,000 stars at a 30-minute cadence, looking for planet transits, looking for dips in the light curve of the star, which hints at the presence of a planet. Now the transit method, sorry, that's the wrong graphic. The transit method is extremely powerful because it tells you the depth of that dip, it tells you the radius of the planet, how often that dip recurs, it tells you the period of the planet. You can get information about its eccentricity in some cases. And via transit timing variations, which I actually won't talk about, you can get information about its mass and other orbital properties. Now with Kepler, finding planets was easy. You can see them by eye. Now this is a typical Kepler light curve hosting a hot Jupiter. Ignore the arrows for now, but what you're focusing on are these dips here. Each of these dips is one transit. The scale is squished, so they look like just little lines. But this is a hot Jupiter with a very large transit depth, and you can see it by eye. Now, the red arrows are pointing at instrumental artifacts. So these are due to the thermal settling of the point spread function of the star on the detector. Because every 30 days, Kepler used to point back to Earth to download data and then put back. And so the heating on the spacecraft will change, and you have these thermal effects. Whatever, they don't affect our ability to find these planets. However, in 2013, Kepler lost 2 of its reaction wheels. Now, reaction wheels are these giant flywheels that allow the spacecraft to keep a steady point in space. They're also what allow the spacecraft to turn. But 2 of them broke, and so the spacecraft no longer had the precise capability of maintaining a fine point. And so the spacecraft would drift. And the engineers realized that one way to correct for this was to flip the spacecraft on its side, point it along the ecliptic, which is the plane of the solar system, and have solar radiation pressure balance the spacecraft, essentially funneling photons around the spacecraft and figure out the perfect orientation that would allow this to be possible. You still need to fire rockets every 6 to 12 hours to bring the pointing back. But suddenly you correct a motion of tens of pixels to a motion of about half a pixel. So the star is slowly doing this on the sky. Big deal, right? It's a pretty big deal. This is a typical K2 light curve that hosts several planets. Now, if this were seen with Kepler, you could pick them out by eye. But the instrumental noise, due to the motion of the spacecraft, seriously compromises its ability to find these planets. So what I've been working on is a method to detrend this data, to try to regain Kepler precision for these stars observed in Q2 so that we can continue to do transit photometry. Now, to bring this back to M dwarfs, one of the really cool things about the fact that Kepler broke was that the observing strategy changed. Now that we're looking along the ecliptic, we actually need to, the engineers need to repoint the spacecraft at a different field every 3 months so that the spacecraft doesn't point at the sun, because the sun's the one. And what that means is that every 3 months, they need a whole set of new targets to look at. And these targets are community driven. And over the past few years, the community has realized that M dwarfs are, in fact, the best targets to look at for these planets and habitable. And so a very large fraction of the stars that K2 is looking at are M dwarfs. So this is my interest in K2. Kepler looked at primarily solar-type stars. But now that K2 is looking at M dwarfs, the potential to find habitable planets is much higher. And so, together with Nick Saunders, I've been working on a model to characterize the systematics on Kepler CCD. And so what you can see is, if you have a star that's completely featureless, it's just emitting the same number of photons constantly through time, what will happen is, as the spacecraft moves, the PSF, the point spread function, the image of the star in the detector, is actually probing different regions of the detector which have different sensitivities. Now this is just due to the way they make CCDs. You can't make a perfect CCD. And so you typically have higher sensitivity near the center of each of the pixels, lower sensitivity near the edges. And as the PSF does this, it ends up imprinting very large systematics on the flux you measure. And so we've been modeling this and correcting for it. What we would like to do is to get an observed signal. Now this is a transit. You can see that it's distorted by some instrumental effect, which in this case is small. We would like to use the data to figure out what this instrumental signal is, subtract it out, and get a clean detrended light curve. And the way we do this is using pixel level decorrelation, where we're using, it's essentially a machine learning model. It's just a linear model where we use functions of the pixels themselves with coefficients that we find a little bit of linear algebra. There's a lot of fancy footwork behind the scenes here, but essentially we're using the data we have. It's completely a data-driven model. We know that the detector, the PSF is probing a ton of pixels. And we have data for all these pixels over a very long amount of time. And so we've used machine learning techniques to deconvolve the instrumental signal and the astrophysics. And so if we do that, we can go back to this K2 light curve. If we detrend it with Everest, we get to something that looks like this. And now you can once again pick out transits by eye. And if you compare this to the earlier Kepler star that I showed you, these light curves are qualitatively similar. So Everest recovers Kepler precision for bright stars. And in fact, if we plot this precision as a function of Kepler magnitude, which is the brightness of the star, now in yellow is the original Kepler distribution. So this is essentially the scatter. Larger values means there's more noise. And this is the magnitude. Larger values means the star is dimmer. It's for astronomers and photographers. And so the Kepler distribution is this yellow distribution, which goes up like this. And now the distribution for K2 light curves you trended with Everest coincides with it up to about 15th magnitude. And then here you can see that there's residual scatter that we're not correcting, but we're still doing extremely well. So we recover the Kepler precision for the brightest stars, which are the ones that we look for planets around anyways. And so this has allowed, together with Ethan Cruzy and Eric Agel, this has allowed the detection of hundreds of more planets in the publicly available K2 light curves, many of which are in multi-planet systems, and some of which are in the habitable zone. So Everest has already allowed the detection of potentially habitable planets. And this is just a sample planet that was below the level of the noise prior to Everest. So moving along to an application, and hopefully it'll now be clear when I talk is in a 7-planet system found orbiting an ultra-cool dwarf, so an extremely low mass entity. It's less than 1/10 the mass of the sun. It's nearby. It's about 12 parsecs away, which means that it can be potentially observed with next-generation telescopes to characterize these planets. 3 or 4 of these planets are in the habitable zone, which makes this extremely interesting for astronomy. This is actually a tie for the largest number of planets in the known exoplanet system. And so it's an awesome system to look at. And in the discovery paper, they used ground-based observations to find these planets and also Spitzer observations. However, the farthest out planet, planet H, was only seen to transit once as of earlier this year. And if you only see one transit, you're not sure it's a planet. It could be something else. It's likely a planet. It looked like a planet. But you don't know its period. And so you don't know whether it's in the habitable zone or not. You don't know anything about its orbit. And so, fortunately, K2 actually observed TRAPPIST-1 earlier this year. And so our goal was to use the K2 light curve, which is 80 days of almost uninterrupted. Is that called? He's off. Any questions?
I can.
Yeah.
Given that through Everest you now have probably a better model of the pixel response function in the camera. If you take that model and then you apply it to the Kepler data, do you get any improvements?
That's a great question. It's something we're looking into. I definitely want to try it. One of the reasons it's complicated is that, on average, you can get what the average pixel sensitivity variation is, but every pixel is different. Mm-hmm. And so you'd have to do it for stars. Like, if the star was observed this part of the detector, I go back to Kepler and look at the star was observed that part of the detector.
It's not like you're lacking in data. I mean, it's a lot more parameters, but you got lots of those.
I think yes. Like all information is good information and can be used. The question is, will it be worth it?
Right. Exactly. Right. Like, I mean,
But,
if you're just looking pure photon information.
so we're looking into it.
Sorry.
Great. Are we good? Can you let me share my screen? Okay. Can you see my screen?
It's looking. We'll get them.
Good. Okay. So back to TRAPPIST-1. So K2 observed TRAPPIST-1, which was extremely well timed, so we could use this to identify the period of planet H and search for other planets in the system. However, this is what the postage stamp of TRAPPIST-1 looks like. A couple things. The target is extremely dim. This is an ultra-cool dwarf, so spectrum peaks in the infrared. Kepler is an optical detector, so it's extremely faint in Kepler band. And if that weren't bad enough, you have all this jitter, all this drift due to the motion of the spacecraft. And so if we look at the raw light curve, it looks something like this. You can see all of these data points kind of below the continuum, all these data points above the continuum. It's not clear at all which ones are transits, which ones are just noise. The scatter is very large. I will tell you that one of the transits of TRAPPIST-1H is in there somewhere. If you have a very keen eye, you might see a dip right there. You guys see that?
Yeah.
Like slightly low. That's D, the largest planet. H is half as big as that. So hopeless. But luckily, ever speed trending worked really well. We also use neighboring stars to be trend, so information from other places on the detector actually help. And now, amazingly, these low outliers remain, the high outliers remain. Every single one of these points below is a transit. Every single one of these points above is a flare, with 1 or 2 exceptions. Extremely rich data set. You can also pick out, in our paper, we also constrained the rotation period of the star, 3.3 days, from the modulation to the star's spot. Here's a family portrait we got of the inner 6 planets with Kepler's short cadence data. Very nice transits for all of them. There's quite a bit of scatter below here, and that's because a lot of transits, since there's so many planets, transits happen at the same time. And so you get residual scatter from other planets' transits. But where's H? Now, we cheated a little because we kind of knew where to look. We only had one transit, so we didn't know what its period was. But Eric Egel, Dan Faberke, and Brice Olivier Denley, part of the TRAPPIST team, they realized that the inner 6 planets had orbital periods that followed an interesting relation. So they followed a Laplace resonance. Now, this is slightly different from a 2-body resonance, which many of you may be familiar with. You have a planet orbiting at 1 orbital period, and then a planet orbiting at twice that orbital period, or 3 times that orbital period, and a commensurate. This is different. This is among 3 bodies. And so you have slightly more complicated relations, but they're still just integers, small integers. And so they realized that all adjacent triplets of planets follow these very simple relations. And so this allowed us to predict what, now this is due to dynamics, right? This is not just numerology. Right? This is an actual physical reason for this to happen. Periodic influence, the companion planets, nudge the planets back into the circle. But to me, it seemed like numerology. I'll show you why in a second. So, interestingly, this relation works for any integers p and q, and so you can play a numbers game and say, oh, if p is 1 and q is 1, then the period I'd expect for h is this. And so only one of these corresponded to windows in the observations that would have been missed by all previous campaigns. In other words, for all these other potential periods, there were times, if you go back in the logs of all the observations, where they should have seen a transit and they didn't. And so based on this dynamical prior and the fact that all of these have been observed and no signal was found, there was really only one place it could be. Now, we could be completely wrong. Right? Again, to me, it seemed like numerology. But as soon as we downloaded the data was made public in March or April, I think. We downloaded the data. It was an insane rush to publish because we knew 4 other teams would be willing to. And so within an hour of downloading the data, we trended it, and then I folded the data on 18.766 days, and I found it. And so I got really, really excited, but also really, really scared. Because, we were looking for it, we see it when we wanted to see it. A thing called confirmation bias. Publish a paper and be wrong. And And so we tried really hard to throw as much statistics as we could at this. And so we can do way better than just plotting and looking for it. We can compute likelihoods. So we can compute the likelihood of the data supporting a transit model at every point in the light curve after subtracting the transits from all the other planets, and look for peaks in that likelihood. And interestingly, all of this is garbage. You don't see anything popping out, or you have these large peaks, but they're not periodic. Okay? What we can do is we know what the depth should be, and so we can condition on the depth. We can penalize fits that suggest other depths. And you'll see that some of these large peaks go away, and that's because those are flares. It turns out that a flare can actually be reasonably fit by an upside down transit, so transits at negative depth. You don't want that. You want to discard those. And so you get something that looks like this. We want to throw away stuff that gives you negative likelihoods and negative delta squares. Still not great. There's still a lot of contamination due to flares, but we can remove that. And maybe, just maybe, you can see that there's this peak, that peak, and then a peak over here, corresponding to the 4 transits of Brown's. Again, not a smoking gun, but those are equally spaced, 18.766 days apart. But we can do even better. We know what the depth was, so we conditioned on it. We also know what the time of transit seen by Spitzer was, and so we can condition that on that as well. And we can just do a grid search over periods. Right? So we know the transit was here, and so for a certain period, I would have transits here, here, and here. I'll stack these likelihoods, I'll just add these likelihoods. And then I'll do that for every possible period of the grid, and plot it, and now we see statistically significant peaks at the correct period of H and its aliases. And so this finally convinced me that, okay, I'm comfortable enough that I'm okay writing this paper. So that was really comforting. If you look at the short cadence data, you can actually see that it is in fact. Now the red line is the model, it's not a fit to the data, it's the model predicted by Spitzer. And it agrees with the data surprisingly. So this told us that we did. If you still don't believe me, Spitzer has since seen it at the right period. So I rest my case. But that was extremely fun application of Everest to a very luminous nebula. Unfortunately, at 18.766 days, TRAPPIST-1H is not in the habitable zone. It's way too cold. It's got an equilibrium temperature of 170 Kelvin. So it is possible that, remember, because the habitable zone evolves, early on when the planet formed, it was actually in the habitable zone for a few million years, a few tens of millions of years. And so if it had liquid water back then, it has since frozen over, but there could be a subsurface ocean on this planet still. I don't know how we would ever figure this out. Actually, I do, but we don't need to get into probably not happening. Okay, so part G, and I cheated because part G has 2 subparts, and so put little moons, planet G there, in each of the subparts. Exo-aurora. So now we're talking about characterizing these planets with future instrumentation. And I'm going to talk about Proxima Centauri b, which is the other hot system, or hot planet for habitability currently. And this planet was discovered last year, spectroscopically, so using radio velocity. It is in the habitable zone of the closest star to the Sun. This is as good as it gets for habitability of exoplanets. Now, this is the discovery data set. So in the radio velocity method, which I haven't talked about, but most of you are familiar with it, you're looking at the wobble of the star, the gravitational tug of the planet on the star. That causes the star to move back and forth. And then if you look at the spectrum of the star, its lines get Doppler shifted. And then you can, with very high precision spectroscopy, you can figure out what the speed of the star is on the sky into another sky plane. And you get a periodic trend, which is due, in this case, to a planet whose mass is consistent with terrestrial. I think it's 1.6 minimum mass.
Yeah.
1.3. Too many numbers. You only get a minimum mass though, because you don't know what the orientation of the planet's orbit in the sky is. It's degenerate with the information in. And so the most likely mass is 1.3, 1.5, but it could be higher. This is awesome. But we should always keep in mind that this is a somewhat low significance detection. And similar planets have been undiscovered before. And so a notorious example is GJ667c, BCDEFGH. So it's a proposed 7-planet system around an M-dwarf. 5 of these planets have since been challenged. Some of them are definitely due to stellar noise, so you have to really understand the noise of the star. Some of them were not found with subsequent searches, so they were not able to be confirmed. And so we need to be very careful about these marginal detections. And so with that in mind, what a lot of us here at VPL worked on was an alternative way to confirm this planet using exo-aurora. So trying to search for the auroral emission of this planet to confirm its existence and characterize its properties. Now this is from one of the press releases, one of the images of the planet. We think it should look more like that. Now that's not quite realistic. An aurora would be concentrated in auroral ovals. But this planet should also have significant air glow, so it might actually glow green. And if you remember earlier in the talk, I talked about how M-dwarfs have extremely high energy radiation, particle radiation as well. And so this can drive strong auroral emission from these planets, particularly for Proxima Centauri b because it's so close to the star. And so if you look at a spectrum, this is a spectrum of Earth. It would be the spectrum of Proxima Centauri b if it were Earth-like. But if it had auroral emission, you would actually see that. So now we're talking about a very, very discrete, very, very thin line, 5577 angstroms, that's in the green part of the spectrum, due to an oxygen transition in the upper atmosphere of this planet. This is why the northern lights look green, if you've ever seen it. It can also look red, that's an oxygen transition in the infrared, red or fluorescent. And so we expect auroral emission of this planet to be very strong. And this is why we think that detecting it might actually work. Right? I said the star is nearby, so you have lots of photons. The star is active, and the planet is close to the star, so you have lots of auroral emission, supposedly. My presentation is like 200 megabytes. Jeez. The star is dim. So the star is particularly dim in the optical where auroral emission peaks. So that's great for contrast. The planet's likely terrestrial, so it could have a oxygen-bearing atmosphere, carbon dioxide form of oxygen. And what's really cool is the planet is so deep in the gravitational potential of the star that its orbital velocity is extremely high. And so the auroral emission of the planet will get Doppler shifted by about 2 angstroms over the course of its orbit, which is huge when you're talking about high precision spectroscopy. You can actually see that if you're able to detect the signal. It's great because it disentangles it from both the stellar emission, potentially at that wavelength, and the Earth's emission. You're staring through the Earth's atmosphere, so you don't want to detect Earth aurora. And what's really cool about detecting it is that it confirms the planet. You can actually get information about the planet's orbit, so you're seeing that Doppler shift. You get information about its mass, its atmosphere, and potentially its magnetic field. Sorry. Okay. So we searched for it. This is what we found. So we stacked 70 hours of high-resolution spectroscopy data using the detection of the planet. We shifted it into the planet's rest frame. So that's these blue lines, that blue window at 5577 angstroms. Red and green are the star's rest frame and the Earth's rest frame, respectively. You can see a little bit of auroral emission from the Earth in green. The reason we need to stack is because this is such a small signal that you can't see it in any individual spectrum. If you stack a ton of them, the signal might emerge. And lo and behold, we find a tiny little peak in the stacked spectrum. It's got a signal to noise ratio of about 4. Which might make you think it's statistically significant, and we found exo-aurora and we have a Nature paper. However, we had to loop over so many different orbital parameters because we don't know what the eccentricity of the planet is, we don't know what its mass is, its inclination. When you do a grid search over so many parameters, you're bound to find something somewhere, right? And so what we can do is, as a control case, we can do the same search somewhere else in the data where we don't expect any emission at all, and we see the same thing. So this is entirely consistent with noise. If you actually do the statistics properly, this is a 0.7 sigma detection. We did not find XOR. And in fact, so Jake and Dave did these calculations for different telescopes. It's kind of hopeless for HARPS, which is what we were using. We would need something like 1 billion hours to find the aurora. So it makes sense we didn't detect. However, with future telescopes, it looks a lot more promising, something on the order of tens of hours, if you have slightly higher auroral strength, maybe during a period of high stellar activity. Okay, this is the last part. So this is something that Jake, myself, and Eric Abel have been working on recently, and we just submitted earlier this week. A novel method to potentially characterize nearby exoplanets. Planet-planet occultations. So, very briefly, back to TRAPPIST-1, James Webb should be able to detect secondary eclipses of the TRAPPIST planets. Now this is, unlike a transit where the planet blocks starlight, a secondary eclipse is the opposite. It's on the other side of the star where the star blocks the planet. Much harder to detect because the planet is so much dimmer. But James Webb is a big telescope. It's looking at the correct wavelengths. Launches next year. And it should be able to detect individual secondary eclipses of the closest in planets. So just to drive that point home, James Webb can detect photons from temperate terrestrial planets from the West Notch response. Okay, but secondary eclipses are well established way of doing exoplanet science. I want to propose something crazy. So this is the TRAPPIST system, to scale. The stars in the center. These are the orbital planes of all the planets, colored accordingly. I want you to pretend that this is an iPhone screen, and you can take a finger and you can pinch and zoom only on the y-axis, like that. So this is still to scale, okay, but the vertical axis is now stretched. The amazing thing about this system is that it is so coplanar and so perfectly aligned with the line of sight to Earth that the planet orbits overlap with each other over a large segment of their orbital period. So I propose that planets actually occult other planets in their orbits very frequently in the system. And so what we can do is, given the orbital parameters we know about the system currently, which are somewhat unconstrained, we don't know their eccentricities too well, mutual inclinations, but we can approach it statistically, right? We can draw from those priors. And we can construct plots like this. This is a diagram of all planet-planet occultations seen from Earth in the TRAPPIST-1 system over the course of 3 years with James Webb. Each dot is a planet-planet occultation. The color corresponds to the occulting body. The size corresponds to the duration. So this would be several hours. This would be about an hour. And the transparency corresponds to the impact parameter, which is kind of a constant for depth of the occultation. These are extremely common. We have on average 1 per Earth day planet-planet occultation. Now, a lot of these are grazing, so not really detectable. But it turns out we have about 40 detectable occultations per Earth year. So it's an extremely rich data set. We're just blocking planet length. And so in principle, the signal strength should be comparable to that of secondary eclipse, which I showed you is potentially detectable in pretty much.
In interpreting this plot, is this like where physically the space group happens, and
Yes.
the ones that are all on the far side, like the star would be blocking?
Exactly, yeah, so the black ones are secondary eclipse, which is why they happen on the far side of the star. The the observers to the ground. And again, the parameters aren't well constrained for the system, and so every time you plot something, drawing from the prior, you get a completely different distribution. But you can approach it statistically. You can look at where in phase these occultations are more frequent, the impact parameters and the durations. And you can see that these are occultations of planet B, for instance. You get several occultations that have durations of about an hour. And so those are potentially detectable. And you know where they peak in phase, and so you kind of know where you should be targeting these observations, even though you don't know precisely when you're going to target. There's similar ones for planet C. I won't go into this too much. But the cool thing is that planet-planet occultations probe the full three-dimensional structure of exoplanet systems. Unlike secondary eclipse, which always happens at the same orbital phase, planet-planet occultations happen anywhere, depending on where the planets are. And so suddenly you have a map of the eccentricities, the inclinations, the neutral inclinations. And this can even break the mass eccentricity degeneracy into these given planet masses. Here's a histogram of what I said earlier. So you have about 20 potentially detectable occultations of planet B and 20 of C in one Earth year. And so we first statistically model the dynamics, including n-body, using an n-body code to model planet-planet interactions. We also came up with a novel integration scheme to compute the light curves of these occultations by exploiting the elliptical symmetry of planets. So in this case, this is a planet without an atmosphere, without significant circulation, where the peak emission is at the substellar point. And so regions of constant brightness on the planet are just ellipses. The integrals of ellipses are analytic. And so you can use this to come up with full light curves for the system, including transits, secondary eclipses, phase curves, and these tiny dips are planet-planet occultations. And here's just one, just for fun. This is what it would look like, an occultation C by planet B. Occultations can give you information about the day-night temperature contrast of the planet. Blue is assuming no contrast, green is assuming maximum contrast. This gives you a shift in the time of occultation depth. It also causes an asymmetry. And so this can be used to build crude surface maps of exoplanets. So with James Webb, we expect individual occultations, go through this relatively quickly, to be right at the noise level. So this is actually 1.4 sigma, which is not statistically significant. But if you stack about 10 of them, you get a statistically significant detection. So this should be possible with James Webb. It should be a slam dunk with Origin Space Telescope, should it ever fly. This is a far infrared, very large space telescope. It's actively pulled to like 4 Kelvin or something. This is what individual ones do. So you have one there, one there, one there, and this is a double secondary eclipse where both means are okay. So that was a lot of information, so let's just recap. We looked at how the evolution of terrestrial planets around them dwarfs is markedly different. Around these luminous stars is markedly different. They could be desiccated and have a lot of oxygen being produced because of the escape process. The flip side of that is that hydrogen-rich planets could lose their envelopes and become somewhat terrestrial. Maybe not in the full sense of the word, but at least water-bearing. We looked at how we can use K2 to find these planets and how we use Everest to detrend these light curves and be able to accuracy geometry. We saw how this allowed us to detect TRAPPIST-1H, characterize the TRAPPIST-1 system more fully. And then I talked about crazy ideas to detect and characterize exoplanets, including exoaurora and planet-planet occultations. So with that, I would like to thank my committee, Rory Barnes, Eric Hagel, Vicki Meadows, David Catley, and Eric Pissarro, and of course the grad students for being super supportive over the past 5 years. My girlfriend Brooke, these two guys here, and Cece for keeping me sane over the past few months, and of course my parents who are watching from Brazil. So, thank you.
All right, thank you, Rodrigo. Questions from the audience?
Jordan? Oh,
Well, some 15 or so years ago, our graduate student and later postdoc Guillermo Gonzalez found that when you look at the hot Jupiters, which was all that was found in the 1990s, that they were much more likely to be seen on stars which had a metal excess of a factor of 2 or 3 compared to the Sun. What about when you go to M dwarfs?
M-dwarfs have a surprising lack of hot Jupiters. The fraction of terrestrial planets on M-dwarfs is much higher.
What about their metallicity? If they have terrestrial planets?
So, as far as
likely to be metal rich?
what I've heard is that metallicity tends to correlate with these gas giants. It doesn't seem to correlate as strongly with terrestrial planets. Like, I think that's current science. Yeah. Oh, Dave. Oh, well, I'll get back to you.
Maybe you want to do that.
Okay. Did you have a question? Oh, sure. So we don't know what the eccentricity is. Planet-planet applications could give you the eccentricity, but you have to find it first. And you don't necessarily know where to look because you don't have the eccentricity. So it's like chicken and the egg issue. Yeah.
So, I thought that you did, orbital is the data
It will be, right? So secondary eclipse measurements, which are possible, are going to constrain very strongly one of the components of the eccentricity. And you combine that with transit time variations, you will get very strong. There will still be degeneracies, but you will get strong constraints of eccentricity, which will help you predict when to look for videos. As for the mutual inclinations, those don't necessarily affect when the planet-planet application occurs. It affects its depth and whether it occurs. And so, if it's too high, the application is just not going to occur because the planets don't overlap. But interestingly, so we ran, Eric Gable ran Monte Carlo simulations where you just draw a very large number of systems with different mutual inclinations and observers at different angles. And you essentially ask, how likely is it for us to see 7 transiting planets around this star for different values of the planet's mutual inclinations? And just the prior probability that it's super hard to get a system this aligned in the first place means that a pathological case where all the planets are aligned in this place, but in this plane, but misaligned in this plane of the sky is extremely unlikely. And so we can use that to statistically constrain the mutual inclinations to less than 0.3 degrees, which essentially means that occultations will occur, but if they occur far from the star, they have a larger lever around, so that will affect the impact around the occultations. And so just measuring the depth of the occultation will tell you which occultations.
So when you actually can take a decent spectrum of some of your planets, like maybe your Neptune has had its hydrogen stripped off, what are you going to look for first? How can you learn about the evolution of these things and their evolutionary pathways?
Yeah. In the far future, I look for signs that hydrodynamic escape has occurred. It's like we like this. So Eddie and I looked at the potential feasibility of looking at absorption and whether that would be strong enough signal to detect exoplanets. mean, it's obviously not currently feasible. Someday.
There's an easier thing to look for.
I'm sure there
that
is.
That we look for on Venus on a regular basis. That gives us a really strong signature that a lot of water escape, and a lot of hydrogen
Haze or
escape,
sulfur.
and a lot of hydrogen escape. And it's real easy to look for. In fact,
Really
it's
is.
not- There you have it. Look for the D to H ratio.
Right.
It's an easy thing to look for. It's just about one of the most common things. And you know that deuterium is a lot harder to strip away
Yeah.
than hydrogen.
And
And so if you look for it,
spectroscopic.
Yeah, you-
Like it's still not.
it's not, it's an easy molecule to detect because it produces a very large spectrum signature
Okay.
in places that we have telescopes that are flying in the next few years, like James Webb, happen to have instruments that are trained for it. So.
So, yeah.
Other things, you mentioned oxygen, 17, 18, anything else you could actually try to go and try to pull apart to try to say, this thing came from this direction instead of that direction.
The density. I mean, that's
Yeah.
that's the first order thing. Right?
Yeah.
If it's extremely low density, then
Yep.
you know that this is empty, like object
Right.
that formed far out. Yeah. So there's lower hanging.
Yep, yep.
Wouldn't it be easier to look at the resonance scattering of Lyman alpha and catch the hydrogen escaping?
No,
That's-
actually the signal's much smaller. I was looking for a really robust signature that would show up in a crummy signal noise or something spectrum or something, right?
So you mentioned that for the planet occultations, JWST would have to stack the occultations to get like a decent signal noise. With it, you've got so many free parameters though. How can you be confident that you're stacking the right occultations? Right, you might be stacking two occultations. Of two
I said
parameters.
stack for lack of time. You should never stack.
Yeah.
Because yeah, I mean, like you don't know, you don't have the parameters constrained well enough to know for sure there's an occultation here. So if suddenly you're stacking 5 occultations and 5 just noise, your signal to noise is terrible.
Well, I was more worried about like maybe you see it by eye that the signal to noise is correct, but you stack 2 or 3, and maybe they're actually different objects
Oh yeah,
that
that's
are occulting.
But that happened with the initial TRAPPIST-1 detection. We thought that there were 3 planets,
Yeah.
but one of them was actually 2 or 3 different planets. But the great thing to do is to use a full photodynamical model and marginalize over, like parameterize everything and marginalize everything and fit all the different spectrums in. So instead of stacking and constraining the stacked depth, you don't stack, but you constrain, given the data sets, you constrain the eccentricities, the orbital parameters, and the temperature mass components. Because all the individual spectrum, so I mean, the other problem with stacking is that the depths could be different, even if they're at the same time. And so you don't want to stack for that reason. But if you analyze them separately, even though they might have different depths and occur at different times, all those data sets have the same hyperparameters in a sense, which are the orbital parameters and the surface parameters. And so if you do this in a more robust way, that can actually bypass the uncertainty of whether the competition. You'll never have to actually test that.
Any other questions?